time-dependent or frequency-dependent properties, which means we have a molecule now in a time-dependent field. Time-dependent, and let's say, to make it a bit easier, uniform field. Which means, for example, or not for example, which means electromagnetic radiation. That is the kind of time-dependent and, let's assume, uniform electromagnetic field we're going to treat. So we have a field now, and in most cases, people only look at the electric component of the electromagnetic field. Although if you're going to do, or if you're interested in circular dichroism, CD spectroscopy, then you actually also need to look at the magnetic component of the field. But let's just keep a field, and that field is now time dependent. And how does that time dependence look like? Well, if you do not assume that it's a monochromatic wave, but it can have different frequencies, then the time dependence has to be described as an integral over all the frequencies, d omega, and the time dependence is then, can then described, or we want to describe it as a cosine. So I have a harmonic oscillating field, which is a superposition of different frequencies. Here in principle sort of continuous. If you only would have one frequency, a monochromatic field, then of course the integral disappears. If you have a few frequencies, well-known frequencies, then instead of an integral you might just have a sum over those frequencies. The most general case is just having an integral over all possible frequencies. And nowadays, where you work with laser pulses, then you really have sort of an integral over all the frequencies which go into that pulse. Now, the fact that I say the field has no space dependence, that means that over our molecule, the field is constant at one particular point of time. So the molecule only sees the oscillation in the field due to the time dependence. But that must mean, I mean, if I look at my molecule, let's say this is my molecule, and I have an electromagnetic wave, then, and that of course has a wavelength, then the wavelength, if I sort of, and this is also some cosine, the wavelength is going to be large compared to the extension of the molecule. So that at a particular point in time, I can assume that sort of here it is constant. This is of course approximation. It's sort of the long wavelength approximation, if you want to call it. One also calls it the dipole approximation, because if you remember from a few weeks ago, 2 weeks ago, when we looked at the potential, the scalar potential in the Hamiltonian, we had the case for a uniform field, and that was interacting with the dipole moment. And if the field is not uniform, if it changes, then we get higher moments also, quadrupole moment and so forth. What we do now here, we approximate, we assume that it's constant, and that means the interaction is going to be via the dipole moment alone. Therefore, it's also called the dipole approximation, dipolar approximation. Right, now I want to rewrite that expression slightly. I want to rewrite that cosine in terms of exponential functions using the Euler expression. So I get I can write that as 1/2 the integral from 0 to infinity. Here my frequency component. And then I get e to the I omega t plus e to the minus I omega t, the omega. That's just using sort of the Euler relation between these exponential and cosine and sine. And having the minus here, I get rid of the sine contribution. And then I can do another thing, because you see I'm integrating from 0 to infinity with omega t and I omega t and minus I omega t. So if I replace, and that's basically two integrals. If I replace in the first part the omega by minus omega, change the variable, change omega to minus omega here, there, and of course in the limits, then I get a minus sign coming from here. And I have integration from 0 to minus infinity. If I turn the integral around, I get rid of the minus sign. And then I actually can combine it into one integral, which now goes from minus infinity to plus infinity. E to the minus I omega t d omega. And that is just the Fourier transform of that. So I mean, this is sort of the physical way to look at the electromagnetic, the time dependence of the electromagnetic field for electromagnetic wave. And this is more convenient for mathematics because that's a Fourier transformation. And later on, I'm going to do another Fourier transformation where I want to use that.